Introduction states a water wheel is a device that uses the flow of water onto the shafts of the wheel to generate power within the rotational movement. A project was given to design a basic water wheel that will generate electricity from a river in the northern range. Due to the fluctuation of water currents by seasonal conditions, a constant flow of water would be determined by a fixed valve that would create a resistance of flow that will be maintained from the input and channel through the output flow. Development of mathematical models will be derived for the elements of fluid, electrical, and mechanical systems of the prototype. This will determine the inflow rate that will affect the rotational speed of the water wheel. A series of transfer functions and Laplace calculations will be used in this project to capture the theoretical results of the system. Trials of experiments will be conducted throughout to compare the physical versus the theoretical values of the model, that is, the flow of water through the resistance valve by the volume measurement of the input to determine an output variable and the moment of inertia on the wheel of the number of rotations created by time.
The theoretical results. The first equation is based on the resistance of the valve. We can rearrange this equation in terms of the output flow rate. Note the difference in height is simply h, as the output is not flowing to another tank. The second equation is modeled after the capacitance of the bucket. By substituting equation 1 into equation 2 and taking Laplace, then rearranging the equation, the following equation was formed. This will be referred to as the final fluid system equation. Linking equation. It was assumed that the instantaneous velocity of the output flow rate is equal to the instantaneous velocity of the wheel, which gives the following equations. Since we have an equation in terms of Hs, this can be substituted into the final fluid system and rearranged to find the transfer function. This is illustrated in the following slide. Resistance of the valve. We need to determine the variables in the transfer function. Resistance is equal to the change in height over the output flow rate. QO is equal to the volume, which in our experiment was fixed to 3.78 liters and 5 liters, divided by the time needed to fill these buckets. The change in height is simply the difference in the water height of the bucket after each respective container was filled. Capacitance of the bucket. Since this bucket was cylindrical in shape, the cross-sectional area of this bucket is equal to the area of a circle, and hence the capacitance of this bucket is equal to the area of a circle, where R is equal to the radius of the bucket. Similarly, a pipe is cylindrical, and hence the cross-sectional area of the pipe is the area of a circle. A step increase of 100 milliliter per second was estimated as one of our input values. By taking Laplace and substituting this into our transfer function, the following equation was formed. This equation can be further simplified. Since tau, the time constant, is equal to resistance multiplied by capacitance, this substitution can be made. The equation can then be rearranged as shown. The Laplace inverse of this equation can then be taken. If we compare our function to our Laplace tables, the function is identical to this format. Hence, the following equation can be used to estimate the angular displacement at a given time t. Time substitutions were made for t values between 0 to 60 seconds, and the following results were obtained. Actual results. The actual input flow rate used can be measured. Since volume of the bucket tank is fixed, we can simply divide the time taken to fill it to determine the input flow rate. Since the wheel is a circle, the distance around the wheel is equal to its circumference. Hence, the total angular displacement is equal to the number of rotations multiplied by the circumference of the wheel divided by the radius of the wheel. Note, some of the theoretical values can now be calculated. For example, the flow rates required for resistance calculations of the valve and the height changes can actually be measured. Furthermore, the cross-sectional area of the pipe and the capacitance of the bucket can be measured, as the respective radii can also be measured. The following table shows the number of rotations recorded for the first step increase at time intervals of 10, 15, and 20 seconds. Using the number of rotations, the following are the actual results of the angular displacement.
Hi, my name is Stephan Thirbenny. In this part of our presentation, I will be talking about the results gathered in our testing and calculation phases. When performing the step increase, time intervals of 10, 15, and 20 seconds were done. We saw that the theoretical and actual testing differ 10 to 15 angular displacements, where the theoretical being the higher value for the table shown. From this table shown, the actual results are between 2 and 14% lower than the theoretical values. Factors affecting results. A number of factors would have played a critical role in not achieving these results. Firstly, the experiment was conducted outdoors. Wind resistance would decrease the number of rotations of the wheel. Strong winds blowing in the opposite direction of the fan would manipulate the input flow rate. Secondly, it is assumed that the input flow rate is consistent throughout the experiment. However, any pressure drops in the source of the water would decrease the flow rate of the input into the system, which would hence decrease the output. Thirdly, the wheel was not secured firmly to the stand. In future constructions, the wheel should be prevented from moving on the x-axis. In our experiment, the wheel would have moved slightly to the left or right. This would decrease the amount of energy being supplied to the wheel and would hence decrease its rotation. In addition, the resistance of the valve was slightly higher than the estimated theoretical value, which would decrease the input into the wheel and hence decrease the output. Fourthly, rotations were not counted and recorded accurately. An attempt was made to minimize this error by taking 3 results and finding its average. The final factor is human error. In the reaction time to manually open a valve or starting a stopwatch would have led to an increase in the times recorded.